K-Tutorial number 3, Defining Lambda++, Lesson 5. In this lesson we see more examples of semantic computational items and how useful they can be. Specifically, we fix the environment-based definition of callCC and give an environment-based definition of the mu construct for recursion. Let us first fix callCC. As discussed in lesson 4, the problem that we noticed there was that we only recover the computation but not the environment when a value was passed to the current continuation. This is quite easy to fix. We modify CC to take both an environment and a computation, and its rules to take a snapshot of the current environment with it and to recover it at invocation time. Let us compile and make sure it works with the callCC env2.lambda program, which should evaluate to 3, not to 4. Note that the CC value, which can be used as a computation item in the K cell, is now quite semantic in nature, pretty much the same as the closures. Let us next add one more closure-like semantic computational item for mu. But before that, let us reuse the semantics of letrec in terms of mu that was defined in lesson 8 of tutorial 1 on lambda. We removed the binder annotation for mu because it is not necessary anymore, since we do not work with substitutions anymore. To save the number of locations needed to evaluate mu_xe, let us replace it with a special closure which already binds x to a fresh location holding the closure itself. Since each time mu_xe is encountered during the evaluation it needs to evaluate e, we conclude that mu closure cannot be a value. We can declare it as either an expression or as a computation. Let's go with the former. Finally, here is the rule unrolling the mu closure. Note that the current environment ρ' needs to be saved before and restored after E is executed, because the fixed point may be invoked from a context with a different environment from the one in which mu_xe was declared. We are done. Let us now compile and krun factorial letrec from lesson 7 in the tutorial 1 on lambda. Recall that in the previous lesson, this program generated a lot of garbage into the store, due to the need to allocate space for the arguments of all those lambda abstractions needed to run the fixed point combinator. Now we need much fewer locations, essentially only locations for the argument of the factorial function, one at each recursive call. Anyway, much better than before. In the next lesson, we wrap up the environment definition of lambda++ and generate its documentation.